Not because of a lack of human ingenuity, not because we cannot dream, but because the universe and physics itself imposes unforgiving limits. Let's start with a thought experiment. Imagine you are holding a small bird in your hands. You open your hands, and the bird flies away. Now imagine trying to catch that bird on another planet, one that is hundreds of millions of kilometers away. You know where it is. You can track its path. You can calculate its exact trajectory. But to reach it with your bare hands is impossible. You can see it, you can predict it, you can even plan meticulously, but your reach is limited by reality. This is exactly the paradox of Mars. We can map it in exquisite detail. We can measure its orbit decades in advance. We can land machines on it with astounding precision. And yet, humans, living, breathing, fragile humans, cannot simply inhabit it at will. We begin our journey with something profoundly ordinary: breathing. You are doing it right now without effort. Air flows in, air flows out. Oxygen binds to hemoglobin in your blood. Carbon dioxide leaves. Your cells carry out their chemical work. You do not carry your atmosphere with you. Earth does it for you. It is free. Now imagine a place where every breath had to be manufactured, recycled, and controlled perfectly. Imagine that a tiny leak no bigger than a coin could be fatal. On Mars, that is reality. Every step, every breath, every movement must be safeguarded by technology. And every technological safeguard has mass energy requirements and potential points of failure. Physics does not forgive errors, and biology does not improvise. Take walking. On Earth, walking is effortless. You lean forward, gravity pulls, friction holds, muscles counterbalance, and you move. Now picture walking on Mars. The gravity is about 38% of Earth's. You weigh less, yes, and you jump higher, but your muscles and bones respond differently over time. The skeletal system depends on stress to maintain density. Astronauts in microgravity lose bone density at about 1% per month. Mars is not microgravity, but the reduced gravity is enough to disrupt the fine balance humans rely on over months or years. That's biology imposing a constraint informed by physics. Then there's radiation. Space is not empty. It is filled with high-energy particles from the sun and cosmic rays from distant supernova. Earth shields us with a thick atmosphere and a magnetic field generated by the movement of molten iron at its core. Mars has almost none of this protection. Its magnetic field is patchy, its atmosphere thin. The radiation that reaches the surface of Mars is biologically significant. Prolonged exposure increases cancer risk, damages the nervous system, and even affects reproductive health. These are not abstract dangers. They are well-measured, well-understood consequences of fundamental physics and biology. And shielding against them requires mass, which requires more energy to move, which in turn requires more fuel. We are back at Newton mercilessly reminding us that momentum does not negotiate. Speaking of momentum, let's talk about energy. To leave Earth, we must overcome its gravitational pull. Escape velocity is 11 kilometers per s. That may sound abstract. So imagine this. Throwing a baseball is easy. Throw a bowling ball with the same force. Harder. Now imagine you want to throw a bowling ball fast enough that it never comes back. That is escape velocity. Now scale up. A ship with humans, water, food, oxygen, life support systems, and redundancy. The energy required is enormous, and chemical rockets are already close to the theoretical energy limits of chemical bonds. Yes, nuclear propulsion exists. Yes, ion drives are promising, but the underlying physics, the scaling of mass and energy, does not vanish. Each kilogram added multiplies the energy requirements. Each problem you try to solve, air, water, radiation, food, adds mass, which demands more fuel, which adds mass, and the loop continues. Time compounds the problem. Even using an efficient home on transfer orbit, the trip takes months. 6 months outward, 6 months return. That is 12 months inside a confined metal tube traveling through a hostile environment with no immediate rescue. On Earth, if something fails, help is hours or days away. On Mars, help is millions of kilometers away. Physics sets the ultimate speed limit, the speed of light, for information transfer. Messages can take up to 20 minutes one way. Decisions must be local. Mistakes cannot be corrected in real time. This is not narrative embellishment. It is a consequence of immutable physical laws. Now, let's step back into history. Because to understand why Mars is unreachable, we must see how physics taught us about motion in the first place. Galileo looked at falling objects and discovered the principle of inertia, that an object in motion remains in motion unless acted upon. It was a revolutionary idea because common sense at the time insisted that motion required constant pushing. Newton then generalized this to his laws of motion and universal gravitation, showing that the same principles that govern falling apples also govern planets orbiting the sun. Kepler's laws were empirical rules describing the heavens, but Newton's laws explained why those rules worked, and so we learned to calculate trajectories, predict orbits, and plan missions with astonishing accuracy. We know exactly where Mars will be decades from now, down to a few kilometers, yet this same understanding shows us why humans cannot easily survive there. Energy, momentum, radiation, time, biology, they all impose constraints. Gravity on Mars is weaker than Earth, but not weak enough to prevent long-term physiological degradation. Radiation from the sun and cosmic rays is intense, and shielding adds mass. Every solution creates new problems. Life support systems must recycle air, water, and nutrients flawlessly. Any imbalance can be catastrophic. The environment gives no margin for error. On Earth, failures are buffered by atmosphere, oceans, magnetic field, and biodiversity. Mars offers none of that. Imagine managing a sealed ecosystem. People, plants, bacteria, water, oxygen, carbon dioxide all must remain in balance for years. A single failure, air contamination, microbial shift, equipment breakdown could doom the entire crew. On Earth, such failures are survivable because we can go outside, find clean air, or wait for help. On Mars, those options vanish. Every era carries extreme consequences. Robots, however, thrive in such environments. They do not breathe. They do not age in the same way. They do not get cancer, and they can endure radiation. The very success of robotic missions to Mars underscores the difficulty for humans. The planet is suitable for machines, but hostile to us. That is the hidden physics truth. Reaching Mars is not just about propulsion or distance. It is about survival within a narrow envelope of physical and biological parameters that humans cannot satisfy without enormous engineering effort. And here we arrive at the conceptual breakthrough. Mars is outside the habitable envelope for humans. Earth is more than a location. It is a life support system. Gravity, atmosphere, magnetic field, temperature, chemistry, ecosystems all work together to allow life to flourish. Remove or alter any of these elements and life is stressed. Remove several, and it is unsustainable. This is not pessimism. It is precise observation, grounded in physics, chemistry, and biology. The laws of nature are different to human dreams. Understanding them honestly gives clarity, not despair. To truly understand why Mars is unreachable, we need to retrace humanity's path to understanding motion and energy, the very principles that make space travel possible, yet simultaneously set its limits. Let's begin with Galileo. He didn't just look at falling objects and wonder why they dropped. He asked questions no one thought to ask. Do heavier objects fall faster? What happens if I roll balls down inclined planes at different speeds? He performed experiments that were conceptually simple but profoundly revealing. Galileo realized that motion had regularity, acceleration was constant, inertia was real, and the universe followed rules that could be measured. These observations laid the foundation for thinking about not just apples falling, but planets orbiting, rockets launching, and eventually humans attempting to leave Earth. Newton took Galileo's insights and fused them with a mathematical elegance that seemed almost magical at the time. His three laws of motion, combined with the law of universal gravitation, unified earthly mechanics with celestial mechanics. The apple falling in a garden and the moon orbiting Earth were governed by the same principles. For the first time, humans could calculate trajectories with confidence. If you wanted to send something to Mars, you could predict exactly where to aim, when to fire your engines, and how to arrive months later with precision measured in kilometers across hundreds of millions of kilometers of space. Yet Newton's laws also revealed the difficulty. A planet is not a fixed target in empty space. Mars moves along an elliptical orbit, Earth moves along its own, and the gravitational pull of the Sun and other planets subtly alter trajectories. Timing is everything. The so-called Hohmann transfer orbit is the most energy-efficient path, but it takes months. Even with perfect calculations, human biology imposes a hard limit. We cannot survive months in a vacuum without immense support. Newton gives the path. Biology enforces the boundary. Let's pause with another thought experiment. Imagine pushing a toy car across a smooth floor. Easy. Now imagine the car is the size of a house, and you must push it across a hill, up and down slopes, through wind resistance and around corners. The same laws apply, but the scale makes it impossible to move with the same effort. Mars is that toy car at cosmic scale. The laws of motion are the same, but the energy and resource requirements explode. We cannot scale ourselves infinitely, and physics refuses to bend. By the 19th century, humans learned to harness Newtonian mechanics in practical ways. Rockets were designed, staged, and tested. Chemical propulsion became an engineering art. Every kilogram mattered. Every fraction of fuel efficiency made a difference. Yet even with the most advanced rockets, we were confronted with the relentless scaling problem. Mass times acceleration demands energy, and energy must come from fuel that itself adds mass. There is no free lunch. Every kilogram of life support system, air, water, food, shielding, adds kilograms of fuel, which adds more fuel, and so on. Engineers can optimize, but they cannot violate the laws of physics. Now let's take a step toward the conceptual breakthrough. Humans are not machines. Machines can endure extremes, tolerate radiation, and operate for years with minimal maintenance. Humans, by contrast, have evolved to survive in a very narrow range of conditions. Gravity around 1 g, pressure around 1 atmosphere, temperatures between roughly 30 and plus 150 degrees C for short periods, and protection from radiation. Alter any of these, and the risk to life escalates dramatically. Mars violates nearly all of these limits simultaneously. The planet's gravity is weaker, its atmosphere is thin, its surface is cold, and radiation is unshielded. Each factor alone is challenging. Together they form a barrier that cannot be overcome with simple engineering. Consider a thought experiment about living in a sealed ecosystem. Imagine a greenhouse capsule containing humans, plants, microbes, air, water, and nutrients. Every system must recycle perfectly. Oxygen must be produced at the same rate it is consumed. Carbon dioxide must be removed at the same rate it accumulates. Water must be purified, stored, and reused. Any imbalance, too much CO2, too little oxygen, bacterial contamination can threaten life. Now scale this from a few people to dozens for months or years, millions of kilometers from Earth without the possibility of resupply. This is not hypothetical. NASA and other agencies have attempted smaller-scale experiments such as Biosphere 2, and even in controlled conditions, failures emerged rapidly. Now imagine adding the stress of radiation, low gravity, and psychological isolation. The physics of life support systems coupled with the biology of humans defines a hard boundary. Radiation is particularly insidious. Earth's magnetic field and atmosphere act as shields, absorbing and deflecting charged particles from the sun and cosmic rays from deep space. Mars lacks a global magnetic field and has a thin atmosphere. Solar storms can deliver doses of radiation lethal to humans within hours if unshielded. Prolonged exposure, as would be required on a months-long mission, increases the probability of cancer, cardiovascular disease, nervous system damage, and genetic mutations. Shielding helps, but the heavier the shielding, the more energy required to transport it, which in turn increases fuel mass, which increases energy demands. Newtonian mechanics again enforces a stubborn limit. Let's explore an intuitive analogy. Imagine trying to build a house in the middle of a desert with no roads. Every brick, every nail, every tool must be carried from thousands of kilometers away. The further you go, the heavier the supply chain becomes. Now imagine that the desert is cold at night, irradiated by sunlight during the day, and subject to deadly sandstorms. Mars is this desert, magnified to cosmic scale. Robots can operate in such conditions. They are expendable, resilient, and do not require air or food. Humans are fragile. The environment enforces its rules, and we must respect them. Let's pause and think about time. Even if we manage the propulsion problem perfectly and carry all life support needs, travel takes months. The delay is more than a nuisance. It is a constraint. Communication with Earth is delayed by up to 20 minutes one way. Emergencies cannot be solved by consulting Earth in real time. Crew members must respond locally with limited resources. This constraint is a direct consequence of the finite speed of light. Physics does not allow instantaneous problem solving. The universe does not wait for human convenience. Another thought experiment helps clarify the challenge. Suppose we attempt to terraform Mars. We try to heat the planet, generate a thicker atmosphere, block radiation, and stabilize temperatures. The energy required is immense. You would need to melt polar ice caps, release greenhouse gases, perhaps redirect comets or asteroids. Even if technically feasible in principle, the scale of energy and time dwarfs human lifespans and resources. Physics enforces the hard cost of planetary engineering, and it is enormous. What emerges from all of this is a deep insight. The problem is not imagination or engineering skill. It is a misalignment between human biology and extraterrestrial environments. Earth is exquisitely tuned for life. Mars is almost the opposite. Life is not easily portable. The universe has exacting rules, and humans are bound by them. Reaching Mars is not a matter of trying harder or spending more money. It is a matter of confronting the unforgiving constraints of physics and biology. This leads us naturally to a philosophical reflection. Humans are wired to dream, explore, and imagine conquest. But understanding reality means respecting limits. The excitement of exploration need not be diminished by these boundaries. It is enriched. Knowing that Mars is effectively unreachable forces us to appreciate the fragility and uniqueness of Earth. It shifts our ambition from planting flags on alien soil to cultivating understanding and stewardship of our home planet. In other words, physics does not constrain wonder. It guides it. And here is the most Feynman-esque twist. The same laws that make robots succeed on Mars, the laws of motion, energy conservation, thermodynamics, radiation physics, also define the boundary for humans. That boundary is not negotiable. It is written in the mathematics of the universe, in the constants of nature, and in the requirements for life as we know it. The lesson is subtle. Triumph is not always about conquest. Sometimes it is about comprehension. We have explored rockets, energy, radiation, and biology. We have traced the historical discoveries from Galileo's inclined planes to Newton's unifying laws. We have confronted the homeland transfer, the relentless scaling of mass and fuel, and the cruel arithmetic of survival in a hostile environment. And now we turn to the broader question. What does this all mean for humans, for our imagination, for our place in the universe? Because physics does not only set limits, it teaches lessons about understanding, wonder, and humility. Think about a moment of insight you have had in your own life. Perhaps it was realizing a pattern in nature, or seeing a mathematical truth emerge from a simple observation, or understanding why something that seemed obvious was in fact subtle. That sensation of a hidden structure being revealed is exactly what physics offers when we confront the challenge of Mars. The planet appears simple, even reachable. It is just a dot in the sky. But when we follow the laws of motion, energy, radiation, and biology, an invisible scaffolding of constraints emerges. This scaffolding is not arbitrary. It is exact, and it explains why what seems possible at first glance is in fact extraordinarily unlikely. Here's a thought experiment to make this tangible. Imagine a child building a tower from blocks. The blocks are of different sizes and weights. At first, the tower grows rapidly, but as it grows taller, it becomes increasingly unstable. One wrong placement, one slight imbalance, and the tower collapses. Human attempts to colonize Mars are like building a tower with inherently unstable blocks. Long travel time, limited energy, fragile life support, radiation, low gravity, isolation, and psychological stress. Each factor alone can be managed. Together they multiply the risk exponentially. The laws of physics and biology dictate the stability of this tower. No amount of optimism changes that. And yet there is beauty in this limitation. Consider what it means that we can understand these challenges. Physics allows us to calculate the energy requirements for Mars travel. Physics allows us to predict radiation exposure, trajectory windows, and environmental hazards. Physics allows us to plan robotic missions with astonishing precision. It is the very rigor that prevents human colonization, which also enables us to explore the universe intellectually and technologically. The truth is empowering. We do not have to set foot on Mars to grasp its mysteries, to study it, and to learn from it. In many ways, understanding the problem is more profound than temporarily visiting the planet. Let's explore a deeper implication. Life on Earth is rare, fragile, and exquisitely adapted. Our biosphere, our atmosphere, our magnetic field, our oceans, all work in harmony to support complex organisms. Mars demonstrates what happens when you remove that delicate balance. Survival becomes exponentially more difficult. The universe is not hostile to curiosity, but it is exacting. Humans are not invincible. Every adaptation, every life support system, every technical solution has to respect the laws of nature. In confronting Mars, we confront the precise requirements for life itself. Another thought experiment. Imagine creating an artificial ecosystem inside a sealed glass sphere. You must provide air, water, food, microbial balance, and temperature control. Even slight miscalculations result in cascading failures. Now imagine that sphere traveling for months through the vacuum of space. Mars is this sphere scaled to planetary dimensions with no outside resupply. Any error in planning, engineering, or biology can be fatal. That is the subtlety of Feynman's insight. Understanding complexity requires honesty about the invisible constraints imposed by physics. Psychology and sociology also cannot be ignored. Humans evolved in communities with social feedback and immediate support. Months in confined quarters far from Earth under constant threat would create extreme stress. Conflicts, cognitive fatigue, and mental deterioration would compound the physical hazards. Physics may define trajectories and energy, but it intersects with biology and sociology to define human limits. This interplay is rarely discussed in popular science, yet it is fundamental to the problem. The universe is not merely a backdrop. It actively shapes what humans can do. Even our dreams of terraforming Mars must be tempered with physics, heating the planet, generating an atmosphere, blocking radiation. These require energy and materials on a scale that is almost incomprehensible. We might imagine comets redirected, greenhouse gases introduced, or solar mirrors deployed. But when calculations are made honestly, the scale dwarfs human capability. The universe permits the imagination, but it does not bend to it. Understanding these limits is not defeatism, it is intellectual freedom. Once we know the boundaries, we can act intelligently within them. Philosophically, this teaches humility. Humans are naturally ambitious. We look outward and dream of expanding across the cosmos. But physics reminds us that boundaries exist. They are not arbitrary or political. They are structural, written into the fabric of the universe. Recognizing them does not diminish ambition, it channels it. Our curiosity becomes more precise, our investigations more profound, our appreciation for life on Earth deeper. To know that Mars is effectively unreachable for humans is to understand what life needs to flourish and what makes Earth extraordinary. Consider the counterintuitive nature of this insight. Many people assume that reaching Mars is primarily a question of engineering. Build bigger rockets, carry more supplies, shield against radiation, and eventually humans will walk on the surface. But the deeper physics tells a different story. Mars is not just distant, it is hostile in fundamental ways that cannot be bypassed. Human survival depends on narrow ranges of gravity, pressure, radiation, and chemical balance. To live there sustainably is not just difficult, it is essentially impossible with foreseeable technology. That is Feynman's shocking insight. The universe has structure, and it enforces that structure rigorously. Yet there is hope, not in colonization, but in understanding. Robots thrive where humans cannot. Satellites orbit and gather data. Rovers traverse the terrain. Spectroscopy and remote sensing reveal mineral composition, weather patterns, and seasonal cycles. Through these tools, Mars teaches us we can study alien worlds, test theories of planetary formation, understand atmospheres, and even learn about the origin of life, all without leaving our own planet. The limit imposed by physics redirects human ambition toward exploration of understanding rather than simple physical presence. Now let's close with a synthesis. Mars is visually close. It is measurable. It is observable. We can calculate its orbit and predict its weather. We can send machines to touch its soil. But humans, fragile biological beings, evolved for Earth, face insurmountable challenges. Radiation, gravity, thin atmosphere, extreme temperatures, isolation, and energy scaling. The laws of physics are exact. They define both the possibility and the impossibility. This is not a story of failure, but of clarity. Science allows us to dream intelligently. It allows us to separate imagination from feasible action. And in doing so, it reveals the extraordinary beauty of Earth, the perfect alignment of conditions that makes life possible. In the end, the shocking insight is this. Understanding Mars and why we cannot inhabit it is more profound than simply standing on it. It teaches us about energy, motion, survival, and the fragile envelope that sustains life. It teaches humility in the face of cosmic scale. It teaches that true exploration is not conquest, but comprehension. Mars is not a destination for humans. It is a teacher, a mirror, a challenge to our understanding. And that, in the spirit of Feynman, is far more wondrous than planting a flag. So when you look up at the night sky and see the red dot glimmering, remember it is more than a planet. It is a demonstration of universal laws, a testament to the fragility of life, and a reminder that understanding the cosmos is the most remarkable journey we can undertake. Physics does not negotiate, it does not compromise, and it does not reward ignorance, but it does reveal truth, and in truth we find a deeper kind of freedom, wonder, and amazement. That is the insight that Feynman would have celebrated. Mars is unreachable, yes, but the journey to understand why is boundless.